Okay, so we'd like to close this session by having any sort of synthetic or integrative conversation. So this is day one called science, but now we're going to move on from this basic science coverage that we had today onto ethical issues and questions of the common good. So here's a chance to get any scientific questions addressed that you might be still thinking about. Jim, do you want to come sit up here with us?
But I'm not a climate scientist.
I know, but
Neither am I.
play one on TV today.
Me too.
Yeah. Come on up here. I have a couple, so I'm going to moderate this session. So I have a couple, I promised that we would collect questions on Twitter, so I have a few. And before I say that, I have to say, what is the best tweet of the day? The best tweet comes from Marcus Walden. I don't know where Marcus is, if he's here. Marcus says, I can't escape chemistry. Presenter is discussing buffers and equilibrium. Buffer homework to do tonight.
You're welcome.
Where to go, Marcus?
Also, I think that another question was, how many, can we put this in Notre Dame terms, sea level rise, acreage lost? I think that you would need about 55 to 60 Americans per year to contribute to one football field's worth of.
Converted to football fields.
Converted to football fields.
Did you say it was 3.5% of the land area?
1,000 square feet per American per year. Anyway, okay. So here I'll ask the first question. This actually comes from an undergraduate who, we have some undergrads who've been doing some reading in preparation for this meeting. She, and I think, David, this follows well on your presentation, she wants to know about short-term versus long-term planning. And, but all of you can answer this question. So how do we set global or national research and application or action priorities for mitigating the effects of climate change, thinking about both the near and the long-term future? And I think she's going with this idea that a lot of the factors that are acting and causing climate change have this sort of long-term implications, but a lot of our policy decisions are in the near term. So how can we account for both the present and the long term together? I know I'm asking a group of scientists a sort of policy question, but putting your science hat on and thinking about long-term decision making, how do we account for that in the way that we make short-term decisions? Joe, you want to start?
Okay. So I will give the engineering perspective. Most of the large engineering projects now, what they do is it's too expensive to design for year 2100. That kind of rate of change of sea level rise, or the rate of change of morphological changes in the ocean, all those things is very difficult to do. So what they do now is just as a general strategy, they basically design for 10 years. So you take the current and you extend for 10 years and see what will be the sea level, and you design for that one in the short term. And that will be much, much cheaper. But these designs now have to have what is called the adaptive design. That has to have a component that if things becoming worse, that you can change the designs, and for the next so many years, I don't know when, you can have a strategy to mitigate these effects. So that's the short-term view the engineers take. And by the way, the engineers have a little bit of a skeptical view. If you look at engineering students, have a skeptical view of the climate change in some sense due to some reason. So this is a much better strategy to keep them happy, as well as keep the climate science, which we predict what is going to happen, and we have to basically believe the best science. And so that is how people do now. Especially the whole Louisiana area now, I'm involved in this San Joaquin River, Sacramento River Delta, so that all these are on adaptive design criteria.
Do any of you others have something to say? Nancy?
I can just react to that. And I think as an ecologist, and one who works in cities, so therefore I'm working with systems that are designed by engineers. And I think one of the things that we have to keep in mind is that maybe the model I mentioned this before, using the past to sort of say what the range of conditions we're going to design for is going to be. So in other words, if we expect that we'll have a certain urban heat island based on Joe's models, then we would design for that amount of warming in terms of shading or how much energy projections we expect or something like that. But what I want to argue is that we need to think about a different model, one that's sort of more responsive to a continually changing environment, and one that maybe monitors and reacts, and perhaps you said this. I would apply that to something like urban stormwater infrastructure, and how that infrastructure planning should incorporate some kind of ability to respond and change design as the environment changes. So that's more about management, planning, and design than it is about political decision-making. I think that it's a huge problem that political decision-making is always fairly short-sighted. And I think it's probably more to the political scientists to speak to that issue than it is to us.
I invite anyone who has a question also to chime in. Please do.
Hi, thanks. Dave Titley, former oceanographer of the Navy and former chief operating officer of NOAA. Just as a question here for the panelists, if you were advising a bright 20-something-year-old person, with or without science, maybe not a science degree, what areas of climate change research would you advise them to go to? Or where do you think, maybe another way to put it is, where do you think the most exciting areas are going to be, say, for the next 1 to 2 decades? So if you were, again, advising somebody, where would be good fields to go to? Thanks.
App development. Just, if he was my kid, I'd want him to develop an app and sell it to Google or somebody, and then I'd be all set. So, for me, I'd say biological responses to CO2 dynamics and to temperature interactions, because I think there's a lot of biology that's interesting that's going to operate, and there's a lot of uncertainty around that, those feedbacks. So I'd work on that.
I think that we need to have a much greater understanding of what the human consequences, the interaction between natural ecological systems and human systems in the built environment in terms of the impacts on those systems, how management, restoration, and design can actually improve their capacity to protect humans from these kinds of things like sea level rise and storm surge and hurricanes and so forth, and some kind of accounting of the value of ecological systems as potentially mitigating against or providing adaptation options for climate change. That would include economic valuation of the value of ecosystem services, but also other kinds of ways of quantifying value to society. So I think if we know that, then we have sort of a little bit better leg to stand on making the case that it's important for us to think about preserving natural systems and their capacity to, it's not limitless, but it's perhaps better than the kinds of design systems we've relied on in the past.
And also, I think it's one of the issues is that we have to somewhat persuade some of the young folks who are in quantitative sciences that this is a real phenomenon. I'm sure that you said that in the morning that the physicists didn't believe 70%. People in quantitative science, they are a little apprehensive of the situation. And 2010, 2011, there was a drop, for the first time, in American Meteorological Society, the membership. Most of the people quoted that it was because the society was embracing climate change. So you can see there is an issue there. So how to persuade people that this is real threat, and although there is certain uncertainty, I really don't know how to do it, but some or other, it's quite important for the young people to realize that this is a real threat to the environment and to themselves. That's a very big issue.
So I think I would suggest to your young person to study the past, because the forecast for the climate change from IPCC is this sort of smooth transition, but if you look at the temperature changes from ice cores from the last ice age, they're not smooth at all. They're very, very jiggly, sort of day after tomorrow-ish. If you go back to the hothouse climates of millions of years ago, they can find palm leaves and alligator teeth in the interiors of continents way in the high latitudes where you can, in a climate model, you can jack up the CO2 and get it warm enough there, but if you do it, by the time they're happy, all the plants in the tropics are just totally dead. And so there's something about heat transport in hot climates that we don't understand very well. Another thing that's really exciting in earth sciences is our ability in the next decade or so to characterize exoplanets. Because this is really mind expanding to all of us. It's so exciting to have other planets to study soon. And I think, planning for the future based on what we anticipate from our models, we're going to get slapped. There's going to be something that we don't anticipate.
I would add a plug for, I'm really interested in this concept of adaptation, so we ought to be able to use this science to making some sort of management decisions that would help reduce the impacts of climate change as they accumulate. But I also wanted to plug Mark Linus's 6 Degrees, which when I read it and asked my students to read it, reminds me that any climate change adaptation that we would talk about being feasible, either economically or technically, is in chapters 1, 2, or 3. Probably not in chapter 4, definitely not in chapter 5 or 6. So even thinking about adaptation reminds us that mitigation needs to be front and center to have any hope of doing scientifically informed adaptation as well.
My name is Amir Pastor. I'm a postdoc here in civil engineering. And my question is kind of a scientific question. So I remember a few years ago that I saw that there is a phase gap between temperature rise and CO2 rise, and that you first get the temperature rise and then get the CO2 rise, and this was kind of one of the claims of the people who didn't believe in the theory which binds CO2 and temperature rise. So is there a good explanation today to these findings, or is there new findings?
This was during the deglaciation. So the depths of the ice age, and then the temperature in Antarctica started to go up, and then the CO2 started to go up. Maybe 800 years later was the published finding. It's not sort of an over and over thing, but just this one event. And then it took 10,000 years for both of them to change. So it's not as though the temperature changed all by itself and then the CO2 is responding to the temperature. It's still a feedback between temperature and CO2. There's no reason to think that the temperature would have warmed if the CO2 hadn't, been there with it. My recollection is that it's difficult. Because the temperature is best diagnosed from composition of the water in the ice, and the CO2 is trapped in bubbles. And there's this offset in age between the two because you have tens of meters of what they call firn, which is snow, but it's still open to gases diffusing in from the atmosphere. So the bubbles close off at some depth below the snow surface, and so there's this difference between the gas age and the ice age that you have to try to correct for. So the 800-year result from a guy named Severinghaus used an exotic measurement in the gas phase to back out when the temperature was recorded in the gas phase so that he would have it from the same samples as the CO2. My recollection is that that actually hasn't stood the test of time, but that's just a curiosity because it's totally possible for the temperature in Antarctica to change for other reasons. It wasn't actually global temperature. There's this thing called the global seesaw. Actually, it started warming in the south first, and then it warmed like crazy in the north all at once, very abruptly, and the south was sort of stagnant. And then it got really cold again, a period called the Younger Dryas. which lasted about 1,000 years, and the temperature in Antarctica started to go up at that point. So it's like this seesaw thing. And the CO2 follows the south much more faithfully than the north, which has got to be a clue for why the CO2 changed. But it wasn't anything that in any way discounted, greenhouse theory or CO2 forcing of climate or anything. This was a red herring, a manufactured, or a puffed up red herring.
Yeah. I have a question also that was asked on Twitter. It said, which this reminds me, how would the climate be changing if humans were not influencing it? Or would it be changing? How would we characterize what the climate is like? And would it just be a steady, over the timescales that we're thinking about that humans care about, would it be a relatively steady phenomenon, or would it be changing at its own accord? Not really the comings and goings of the ice age, but shorter time horizons.
There's a figure from the IPCC report that I could pull up. It'd take 2 seconds if you want to see it.
Yeah, go for it.
But it shows the effect of, this will take a second because I'm shut down. It shows what models predict from the last sort of 100 years of climate when you tell them or don't tell them about the greenhouse gas forcing. And so up to about 1970 or something, they're all the same. Even though CO2 was rising, it apparently wasn't significant. But then the models, when told about the CO2, start to rise, and the others don't, and the real temperatures rise. So really, the smoking gun for human impact on climate is the temperatures since like 1970, which I think Ram also said this morning. It's not the medieval warm period or the ice ages or anything else, but just the last couple of decades. Let me take this up. Maybe you could take another question while I'm...
And that figure shows the
Just
continued
also-
ongoing influence of things like volcanoes and other natural processes, but it doesn't account for this rapid increase.
Well, the fact is that climate does change, and
Right.
it's the additional change that is of concern, the additional change from humans. And I think we also see 1960, 1970 as a period of inflection on a number of things. As pointed out in that graph that I showed of the Anthropocene, this sort of large number of changes in a very large number of parameters that happened around that time, or accelerated around that time.
Bruno, you want to ask your question while he pulls up this slide?
Yes. I have a question, but I don't know if this is good for this day or for the policy day, but anyway. So
Ask it both times.
Yeah.
I kind of think that the climate change issue is not anymore a science issue. And for how many years has that been the case? Maybe 20, 30 years? It is neither a technology issue, because we kind of know what we need to do, and the technology to do that, it's already there since maybe 10 years or so. So maybe it's an implementation issue or an awareness issue, and I think it's an awareness issue. So I'm wondering if there is any other case in the history of humankind that we face something similar. So maybe the ozone layer, how it was not relevant for the people, but we scientists realized that it was a big problem, so something changed and we fixed it. If you know of any other case that we can take as a role model of what we should do or what we shouldn't do, could be another example of what happened or we didn't do anything.
I'm sort of thinking about there was a big controversy about the role of different nutrients in causing eutrophication, this overgreening of lakes, and how lakes got all slimy and green during the 70s. And there was a big public discussion then, also mitigated by industries that were, certain scientists were saying it was phosphorus is the problem, but the detergent agencies were arguing it's carbon, it's organic carbon, it's sewage, it's the carbon that's the problem, it's not the phosphorus the problem. But it will all ultimately end up being solved as far as the scientific question behind it was by an experiment done in Canada where they divided a lake in half, and one half got carbon and nitrogen, the other half got carbon, nitrogen, and phosphorus. And there's this famous picture of this lake where it's just nasty green on one side, the side with the phosphorus, the other side is fine. And so that was sort of like the critical experiment that was able to be run. That's really and I call that the most powerful picture in the history of science or history of the environmental movement, because after that, things started to happen, right? So advanced wastewater treatment was implemented, phosphate detergent bans took place, and so it really was an issue where the science was done, here it is, and then there was the dialogue went on. The scientists did what the critical, and then it's not clear what it will take if we haven't done. I mean, I've seen many studies that convince me scientifically that climate change is happening. It's caused by humans, and et cetera, et cetera. We saw a number of graphs already this morning that make you really, pretty convincing to me. Yeah, that's right. So I don't think we're in that world anymore. Like, I'm sorry I said this morning, I don't think we're in that world anymore where that kind of scientific information, people aren't looking for that kind of information to make their decision, because their decisions in many cases have been made. They've been made regardless of the data. It's
But
not
Jimmy,
the data.
You know what, the fix is a little easier in that case.
That's right. So it
And,
was, again, with CFCs, the fix was relatively narrow, right? There was a
It's
very
relatively
narrow.
It's not costly.
That's right.
It's not being, threatening our
So we
very
may have no
lifestyle.
examples like this to go on.
Plus, the original prediction for ozone depletion was for gradual depletion, which would be sort of on top of natural variability, and so lots of room for argument. But then the ozone hole happened, which was actually kind of irrelevant for the larger picture, but it showed for sure that it was a smoking gun, and it showed for sure that that chemistry that they were talking about was real.
We have a discussion group here at Notre Dame among a variety of faculty across different disciplines talking about sustainability issues, and we often talk about climate. And I think one thing that happens frequently is, and some of them are sitting in this room, the humanists and social scientists will look at the physical scientists and say, okay, you guys, so this is a problem in your neck of the woods, so please guide us to solving it. And I think a lot of the physical scientists look over at the social scientists and the humanists and say, okay, well, we've done science, so you guys, can you help us convince, explain it, compel people, come up with policy solutions? And undoubtedly the answer is some of both. I still think there's a role for science. There's a lot to be known. There's certainly a lot to be known about what types of solutions are feasible, but at the same time, we've covered the basic territory. The big questions are known, and it is time for social action. I think would you all agree with that sentiment?
Yes.
Yes.
I think we can help, though. I mean, you made this point very, very well in your comments in the earlier panel. We can do a better job of communicating, and so visualization, the kinds of talking in plain language about what's happening. This has been a real strong emphasis of the National Climate Assessment, is to put these things in plain language that people can understand. It isn't just a lot of jargon that confuse people and make them think that we're obfuscating.
But again, going back to those, the science, the climate change communication psychology literature, of which I read very little of, but you guys probably know much more than I do. It really is, it's not so much the graph as often as who's showing it.
Another issue, especially for Bruno, is that not like other issues, here climate is a 30-year average. So what the numbers you are getting is measured at 10-meter height and 30-year average. So it's very difficult just to look at one observation point and compare with the 30-year average. So that becomes a very difficult issue. Today it may be very cold, but it doesn't imply climate change is not happening because you are giving the 30-year average in the models. It's an issue.
So
David,
I
I'll
would
give you
say-
oh, sorry,
Yeah.
go ahead. Make your point there, and then I was going to let you talk about your slide, and then I was going to close it up.
Okay, well, the slide just says what I said. It's the pink ones are the ones, the model results when you tell them about CO2, and the green or blue ones are where you don't tell them about the CO2, and the fact that you have to have the CO2 to explain the warming since the 70s, that's the smoking gun. I would say that I don't think, certainly scientists can always do a better job of explaining things, but I don't think the limiting nutrients is science, exposition. If you throw a scientist into a lake, it's not going to turn green. I think.
Well, because you're full of phosphorus, but.
I think what's going to convince people is when hurricanes and droughts destroy their country, and we just have to be here.
But I think I would say but I think one point of what's trying to happen here is how to change the terms of it, so that doesn't take that, right? So we don't have to get to that point where we can have where the moral persuasion comes to the fore and communicates to people who are well-meaning, right? The deniers, they're mostly good people, right? They're not evil, the ones that I get email from. they're good guys. They really care. They care about, but what is it that is going on out there that permits this discourse where people will, that permits it, or facilitates it, that creates an arena where, and he's, again, bring this back to Notre Dame. So I'm trained here and came from the Notre Dame tradition, which is we're not allowed, everything we do is bound up with our moral and ethical obligations to others. And my acquaintances and my friends from the past here in the same way, right? So we have the same sort of moral and ethical obligations to people of the present, and the people of the future. And I think there's a lot that we can communicate about our obligations to each other. But as a scientist, it's not something that I'm especially charged with doing.
Right.
There are many other people in this room or on this campus who are in a position who are charged with those kind of duties of communicating our moral and ethical obligations to people of the present and the future in whatever faith tradition we're in. And I'm hoping, one reason I wanted so much to talk to Jessica about coming to this conference is that I hope that my alma mater will play a role in changing the tone of the dialogue around this issue.
And we're going to spend lots of time tomorrow talking about the people of today and the people of the future. And before we break, I need to remind you of 2 events still this evening. One is Mass, celebrated by Father Coleman, who was here briefly. In 5 minutes.
Oh my.
Run! Is at the Basilica, which is a lovely place. And movie tonight at 8 o'clock, followed by discussion. Led by Dan Misla. Great, Dan, thank you very much. So we'll see you tomorrow morning.